For
the dates?
For the dates, when we need to finish.
Yep, finals week is 10th through 14th.
Okay. So I suggest the following plan. So today and next week we'll do projects. The Wednesday 5th, there will be like submission of written reports, and on the exam week we'll select a day that is comfortable for everyone to make presentations. Any protests, or it's more or less okay? Okay, how are you? Very good. How are you? Very good, thanks. So log in, open Matlab, download code, start running it, and then we'll give some comments. So there will be 2 in-class lectures on 26 May 3rd. Well, today, next week, and on the May 5th, there will be written report submitted. So here is your sign-up sheet, and I think for Tyler there is no chance other than to accept the lower right cell, which could be the hardest, but I'll try my best to help. Tyler, are you okay?
Yeah, I'm okay.
Okay, then I'm writing on your behalf. Okay, and what we are going to do today. So by now you do have an instrument that should work, and you are aware of how what it does. And we are coming to the stage of accumulating, like collecting data for your reports according to your votes here. So for CHEM759 and CHEM759, basically you just set up the value of the spin-spin conflict, run the code, and just store the heat capacity or whatever figures come out. Later on, like what to expect. You probably know the rules of gaming the research activity because you are doing it for life. So just arranging figures that they look nice and describe what is in them, and after describing objective observations from the figure, try to make some conclusions. Right? So this we have about 2 weeks for that, but if you do everything now or collect as much data as possible today, it will be for your benefit. And there is a chance to complete everything just sitting in the class, not doing things at home or minimizing things at home. So for those who are scanning temperature, you just set up the value of coupling that is according to your votes, run the code and save images as figures or as data, and maybe start collecting them into the PowerPoint or Microsoft Word document, because later on you will try to describe what you can observe. Quick comments. If you're doing positive and negative, we can just give this value. If you are, let me bring here, if you are fast, then literal value of 001 may bring numeric instability. So you better put something like very small but non-zero, something like that. and try to see what happens. So you can collect energy as function of temperature and heat capacity as function of energy, and make sure that they look nice. There are ways made like line thicker and background white, and I can assist if needed. If you think that it is too simple task, if you want to do extra, you can try to check a couple of other values of magnetic field. And when you increase magnetic field, it will be boring. But if you make it smaller and smaller, the results may become, on one hand, scary, means like numerical instability with errors. On the other hand, it will be more scientifically available. Okay, so any questions from CHEM verifiers and issue?
Not right now.
Yes, and I'm going to give like suggestions and some comments to everyone, and then I will make visits to the seat in class or ask you to share screen. So please try,
Okay.
and if there will be questions or how to say complaints, you'll try to fix them collectively.
Okay.
Okay, yeah, thank you. So for Xinjiang, Payman, and Tyler, I'll try to give comment and explain what to do mostly next week. But I'll try to do something today, but objectively it's a little hard. And instead I'll invest most of the time today to help Sophie, Crystal, and John. In fact, no one needs help. You have everything, but just to make you to feel more comfortable, or just show something and make sure that you feel comfortable with what you're doing. So I'll go over the density of states, like how it is computed, how it is visualized, and how to interpret, so that you can go forward for collecting data. And for Xinjiang, Payman, and Tyler, there will be a little modification of the code. So before I go to details with density of states, I'll just show what will be the modification for scanning of magnetic field, so that if you're impatient and you feel yourself strong to modify code yourself, please go ahead. So currently, we set up temperature times Boltzmann constant, some prefactors time scanning variable, which just goes with its dimensionless infinitesimal stuff that goes from 0 to whatever. For the magnetic field, I'll type it here, but I'm not going to run and debug. So So basically, these 3 lines change will make the day for those who selected lowest row, Young, Payman, and Tyler. You can try and see what happens, but when I feel a little bit more debugging is needed, especially in the way how the variables are saved. So there will be nothing more in principle, but one needs to meditate and do it without rush, which is hard to do in collective editing. So I will remove these changes for now, in case we need to run. And we'll shortly go to the subject for Sahih, Crystal, and John. Any general comments, suggestions, criticism about organization of our
when you changed line 107 and put it the percent sign in front of it, I think that was originally just regular or the B, you added a line. Okay, never mind.
Yes, so if for those who selected scan magnetic field, we need to scan over different values of magnetic field, like you are putting your sample inside your cell with strong magnet and vary voltage so that magnetic field increases and see response of the system. For first two rows, we don't care about the scanning of magnetic field, we just set it as a constant. So no other questions or criticisms? Okay. Then I'll probably go over the recent changes of the code that didn't touch the central part, but it just modifies visualization so that the density of states can be seen in the best possible way. And then we'll probably set up one-to-one visits. So this is kind of figure that is expected, and the set of parameters here corresponds to the problem, the selection of John. So if he's not here, I will be his substitute today. So there are several peaks, and each peak corresponds to a certain number of unpaired spins, where the most of the configurations have strong degeneracy. And the stuff on the y-axis is not a number in the literal sense. It is not linear, it is logarithmic scale, because they differ like by 4 order of magnitudes. So some are strongly degenerate, some are not. So in the recent version of the there is a little addition, and I'm going to go over it and then demonstrate how it works. So if you selected the research subject in the first row, you just run the code and with certain parameters, and then report density of states and try analyze what are the microstates behind each of the peaks and how the certain shape of the density of states eventually affect observables like heat capacity and magnetization. So at earlier stage of the code, their variable states was created and saved. Let me check. Yes, so line 361, the variable states include the number of iteration, number of the sample, the energy of microstates converted from atomic units into volts. And the last column, I decided not to use it, but just in case it is logarithm of the Boltzmann factor. So it's how much given microstate is populated by temperature. So this is a list of all microstates that we randomly screen. I'm going back to the end of the script. So this line is just in case I do not want to read the rest of the code. It measures the number of records. So by taking size, it populates the variable NDOS with how many records are in this array. Then this minimal and maximal, they just take energy of the lowest available microstate and energy of most energy, the highest energy among available microstates. Why it is needed? Because later, right now, the question is not about doing calculation at the next few lines of our activity, but how to visualize and interpret. So if you want to visualize it reasonably, we do not want to visualize white spots where there are no data. So we need to start from minimal energy and at the maximal energy plus a little margin. So here this range is identified. Number of grid points. So the continuous lines, in fact, are a collection of individual points, individual dots. And we just decide what will be the resolution. So how many individual dots will be set up along x-axis to sample all this dependence. So if you are not happy with visual presentation of the figure, you can increase, like if your screen has more than 2000 pixels. If it is not, then there is no reason to use more because it still will be not visible to human eye. Step is just energy offset between nearest points along energy. And then this E grid, again, it has nothing to do with science. It's only the way how to visualize stuff. So we start minimal times some factor, a little bit lower than minimal. We end at maximum a little bit later than maximum, and we increment the grid points by this step. Then we declare the variable for density of states. So it should be the same length, same size as this grid points, but before we start populating, it's empty. And the width parameter here is how wide is individual line. So it's FWA, it's like how you measure spectral length, what its width at the midpoint. And you also can modify this parameter. I just took it 10 times bigger than step, but it's quite arbitrary. Okay, so now preparation is done, and we are practicing to make a scan once again over all microstates that we have preliminarily stored. Scan over stored microstates. And then each microstate, where energy is saved in the column 2, number I, is subtracted from this grid line and practiced and placed into the exponential with like Gaussian function. And since the y-axis is arbitrary, I just was lazy to put correct factors in front. They will not change the how the figure would look like. But if by some reason you feel yourself meticulous, you can look for the precise factor for Gaussian function and put it here. So each microstate contributes a peak that looks like this Gaussian function. And then after it is done, one just plots it. So instead of plotting those, one plots the logarithm, or one can plot DOS and then change it to the logarithmic scale. So we can figure, then copy paste. So first, as a little example, I'll plot DOS without this logarithm, and it's like, well, not 4 but 3 orders of magnitude. It's like how much degenerate states are, and those states which can be microstates, which can be critically important, they are not visible on this scale. So one can either type and then modify axis to focus on the correct range, or one can go as we originally did, and then there should be ways to modify so if you select arrow, double click on figure, and then there are ways to modify parameters, and one of these parameters, if you look through, will be to make it log scale instead of linear. I will not try to find it right now. It's just will be a waste of time. But instead I will do log and then do axis. So from so 4 numbers are here. First is where we start on the x-axis. Second is where we end at the x-axis, and here where we start on y-axis. Here where we end on y-axis. So if I put bigger number here, it will be not as visual, less interesting to observe. Any questions by this point? And if you select to use Matlab instead of Origin or Excel for plotting, one can add these commands, and they will bring the labels. And there are ways to like either screenshot or export figure. So when we were discussing this thing in the past, I was showing image like this. Did I? Well, even if I didn't. So this image is done for ferromagnetic case for negative value of the parameter J. and you see that there is ground state isolated in then nothing, and then this wing is shifted to the right. When we practiced when we practice this today for positive value of G, it looks opposite. So there is one isolated state, which is absolute maximum, and then the wing shifted in the opposite direction. So one may need to try analyzing why it happens and what are the microstates in this in the center, in the left, in the right. Why it is shifted one or the other way. So it's basically the actual research contributing to overall investigation of this problem. So if you are really busy and limited in time, just do one figure with good explanation. If you are hungry for more activity, you may try to repeat it. That's okay. That's okay. I'm finishing the stuff that is part of your project, but you wrote it in the record.
Yes.
So I was your substitute. I was your substitute. I was showing data that you are expected to generate.
Thank you.
So if you are hungry for knowledge and for these activities, you can redo it several times for the value of J that you have already selected, but try different values of magnetic field. And when if you make it, so what to expect? I can show it so that there are some expectations, but you can prove it if they're correct. So if you increase magnetic field, the splitting, Zeeman splitting of the states will be broader, and the figure will cover broader range. If you take magnetic fields smaller, it will be narrower, the peaks will coincide with each other, and also the most interesting on one hand and dangerous and challenging from numerical point of view is that this envelope maximum will completely shift to the leftmost side, or in other words, this ground state, this minimal energy will be non-resolved, will be mixed with this maximum, and it will result in a situation when there is no well-defined energy minimum. So it's most interesting and most numerical state. So this result, this density of states for positive J for antiparamagnetic piece is basically what is expected from job. And you just you want to see here a little more, you can download the script from the email and just run and see if you get something like that and export. And then try to either screenshot or exporting data and towards the report, collecting figures and explaining.
What is a good range for the magnet, like for change the magnetic field? Like what would be good ones to set it to?
So if someone is being asked a question and do not know what to answer and wants just to provoke time, the typical is, oh, what a good question. Another way, values of magnetic field can be big, can be small, but seriously, there is another part of this project that I do not think you have time and energy to complete. But when it's not complicated, but one needs to be very sober and concentrated to make connection of the parameters to real world. It is possible, but it will not change the main conclusion. So one can go from atomic unions to like Gauss or Tesla, find what is typically used in experiment and keep it there. for all parameters. And this J pattern can be also borrowed from literature or computed ab initio, but we will be good without it. So for the values of the parameters, it is not as important their absolute values, but it is important their relative values. So right now, B and J are, the ratio is 1. And one can take B 10 times smaller than J, 100 times smaller than J. Or maybe 10 times bigger. And this will be enough. Because one run takes like 10, 20 minutes and your time is pressured. So if you do 3 runs, maybe it will be enough food for thought to analyze and describe.
Okay.
Okay.
Thank you.
Yes. Huh? Oh yeah. Okay. So I'll check if there are general questions, and then I'll start one-to-one visits. Okay. If then if there are
one last question. Then you said for J, don't ever set it completely equal to 0. Just set it very, very small and slightly above.
Yes. You can try and take responsibility for consequences. So I'll show not literally because running will take time. So here I did run the code for positive J, which is a task for John, Ichi, and Tyler. And here are results for total energy. You see it has some numerical errors.
You stopped sharing your screen.
Oh, thank you. I was about to go on the tour for the seats. Therefore, I stopped sharing. Yeah. So here is energy, and at lower energies, it has noticeable instability and numerical errors. Here is magnetization. Here the error is bigger than the result itself. And for the heat capacity, it looks reasonable at higher temperatures, but as temperature goes to 0, it gets instability even if one tries to practice fine. So it is objective limitations for this methodology, and one also discussed why it happens. Whether one can fix it by increasing the number of samples, or there are some objective errors that cannot be fixed by this methodology. So for the positive J for antiferromagnetics, it is known to work this way. But if you try to put J literally equal to 0, such numerical instabilities like large deviation from central line seem to increase. And if instead of absolute 0 you just put smaller number, it fixes the problem. One can also at least practice it, or at most analyze what is the reason of the instability. Maybe somewhere in the code, explicitly or implicitly, something is divided by J in one of the procedures, and division by 0 makes instability. Make sense?
Yep.
Okay. So, before I go for a tour, I'll set up everyone as a co-host.
You can also, if you just go to like the share screen button, there's like a little arrow. If you click the properties, you can just change it that way too, where everyone can share.
Okay, I'll try it.
Yeah, go advanced, little arrow, advanced sharing options. And who can share? All participants.
there is a way to make all participants?
Yep, everyone can share. If you click the where your green share screen is on yours, there's a little arrow right beside it on that button. If you click the little up arrow.
So
I can just set it, but yeah, it's advanced sharing options and then all participants.
Multiple participants can share simultaneously?
The two who can share, I just switched them to all participants and all participants under advanced sharing options. Like your last option is advanced sharing. I just changed it for you.
Who can share? All participants.
Now everyone
Okay.
can share.
Okay, yeah, thank you. Okay, so I'll first visit everyone who is physically in the class and then go one-to-one to those who are online. So please try to run and share either errors or success, whatever we need to discuss. Just run and see the difference. Or visit someone else in this.
1, 2, 3, 4.
Okay, so we just including this below. I hope that it. So it's this winners then here we are spaced So please show me the oh, you copy paste the whole page. Oh, interesting. There is a different thing. Changes. Yeah. It's the relationship. So it was looking for Yes, well, some you yourself because based on these results that you will generate improvement. So it is what you used to do in the our experience in this project. Not today, in 2 weeks. For you, 2 weeks to describe them. It's like for the 4 pages of text.
Crystal, can I ask you one question?
Sure.
So for the DOS, which line do we need to use? Do you know? Like to make the graph?
What do you mean? Say it again, Sohi.
Oh, so from the Matlab to make a graph, do you know which line
Just run the whole code. First we gotta change up in our lines 1 through 6.
yeah, so luckily oh yeah.
So we have to change your J because you're negative. So
Yeah,
you gotta-
negative, yeah.
Yep. And then just click that run button up on the top where it says green run, and it runs the whole thing. And it takes about 10 minutes, and then you get about 7 graphs to spit out at you.
And sorry. So after changing that, like what we need to do? Like
Click on the up on the top of the screen. There's a run button, like a little arrow, looks like a place sign. Click the green run button, and then just let it think.
Oh, really?
Yep. And then that's where he says we can try different values of J after this one runs. And then different values of B, but that's all.
Okay.
Are you getting like little pop-ups now where in the bottom screen it's saying like A equals 1, A equals 2, like slowly? Like 3 A's and then that equal, and then it just counts off 1 onward in like your command window? It might take a moment.
Is that what's supposed to happen? Oh, I see that.
Yeah, it looks like
Yeah, once it hits 100, you'll get graphs. Once your A equals 100, then your graphs spit out at you, because mine just spit out at me.
Oh, okay.
I haven't figured out what AAA equals yet, or what it represents, but when it hits 100, your stuff spits out at you. I figured that much out.
Makes sense. Like then did you get like figure 1 to figure 6 next to
Yep,
maybe
figure 1 to figure 6, yep.
Yep. Okay, thank you.
No worries. And then I'm just copying them into a Word doc with like what I set my J equal to, so that way I can kind of keep a running tally. Because if you, once your figures pop up, if you go to the edit on that figure, you can copy figure and paste it.
Oh. Okay. Because I usually do just capture it because to me that's easier and I can use.
Yeah, this way you don't have to crop it. I did the like print screen for a while too until I figured out that it does that, and then you don't have this weird gray thing going on. I figure we gotta put them in a Word doc eventually anyway, so. I'll have to check my people probably fix it as well, but
Now you can collect as much data as in the final report. You can put on the those explain. It's not possible. That's it.
Yeah, actually, I have a question.
Yes.
So, I wouldn't get away to say
Just make screenshot and put it in the report. Okay, let's go one to one for online. So, Crystal, would you like to be the first?
sure. So I ran the Matlab. First questions I had from it. What does AAA stand for? Like, I know once it hits 100 from based on like just doing a couple times that it means that when you hit 100 it generates it out, but what is the AAA actually represent?
Okay, can you slowly scroll the code down?
It starts from
Oh,
one.
no, Crystal, I have.
Oh, the command lines. Okay.
Not command lines. The panel with this one with the script text.
Yeah.
Scroll until please keep scrolling until I tell stop. Scroll. Yeah.
Oh,
Stop.
there.
Yeah, stop. So you see, temperature is in line 106. Temperature is defined in terms of scan variable. And I did, nothing is changed in principle, but in the previous version of the code, our temperature was going in the constant step.
Okay. So
and now
like
through this AAA variable, AA just changes in the range, but then the scan through this little exponential in line 103, the grid points for temperature are more dense closer to 0 and less dense closer to infinity. So because most interesting phenomena happens at cryogenic low temperature, we need to have more denser spacing of samples.
okay.
Make sense?
Yes.
Okay.
And then
so next question.
Set it up so that I put it because you said 1 to 1 for the first one, so I made it, and then you said it's as close to 0 without 0. Is the with like 6 zeros and a 1 good, or do you want more zeros?
Maybe less. Maybe less. Show your figures, please.
Yep.
Keep scrolling.
They look kind of messy.
Yes.
But then that one doesn't look so bad.
Oh, this one is better. So enough. Let me say something. Your time is very precious resource. So let's not overuse it. So you do not spend more than like half an hour or hour for the project per week or something like that. So if your time would be cheap, I would suggest you
This
to
just involves the background running, so it's okay.
yeah. If you would have unlimited resources of your time, I would suggest just rerun it again and again with little change of parameters. But it is not physically reasonable. It's not efficient. So you already got that at this too small value. It's kind of strange. Now remove a couple of zeros. Instead of 6 zeros, keep only 4 and check what happens. And when you will have successful run, you will there will be 2 reference points from the literature and from so to say Wikipedia and from our lectures that you may fit into. Your results may fit into. So first, the energy will be like tangential of tangent hyperbolic. The heat capacity will have a peak. It will be ugly with noise, but it should have some a peak. And magnetization for 0J should behave like 1 over temperature, which is Curie law from paramagnetics.
Okay.
So just try to catch it, but the main thing you are doing is the density of states. And notice, look at the density of states that you're showing. Your x-axis now goes 10 minus 5. So it is, they're really narrow. They have, it's 10 to the minus 5. It is a fraction, it's like fraction of, it's less than 1 Kelvin. So all states have energy offset less than 1 Kelvin. They are really close. So it looks very similar to what it was before. But if one catches this 10 to minus 5 here, it means they're basically all degenerate.
Okay.
And as soon as this degeneracy is partially lifted due to a little bit bigger than 0 J value, the figures will become more normal.
Okay.
Okay. Any other emerging questions?
Yes. What does this graph represent? Like the last one, the figure 6 that pops out.
I think it is magnetization, but if it is not labeled, I can go over the script and email to everyone what it is. But right now we have very short time. I have a meeting starting in like 9 minutes, so I want to visit with everyone.
Okay.
So any other emergent questions?
No, because you says just do once I find my J to do, then set my B to be 10 times, 100 times smaller, 10 times and 100 times bigger, and make those
Yes.
bar graphs.
Yes. Okay, you can stop sharing. Chamali, would you like to share?
Yes, sure.
Thank you.
So I ran with my J value set to a negative value, just
Yep.
negative J, and got these figures. What's the first one?
Huh?
The heat capacity.
Very good, very good. You see how smooth it is. It's good, stable results. Okay, keep going.
And so, yeah.
So if you do not like one or another line, you can click on this little arrow.
What's that?
Arrow. So arrow at the top.
The
Up, yeah. click on arrow. Now
Okay.
click on the line that you do not like that has too much noise. Click on the line. Click on the line. Blue line. Click on the blue line.
Blue line.
Yeah. Click. Click. No, click on the line.
Okay.
And now hit the button delete. Hit the button delete on your keyboard. No, no.
On your keyboard, where your letters are.
On the keyboard.
The one above your backspace. On your,
Backspace will work as well.
like where you type.
Okay.
Hit the backspace
Oh,
like if you're
oh my God. I lost the figure.
and then click backspace.
Oh shit.
Oh. Actually, I think we just click.
Oh, yeah. So you see, you can edit your figure and erase lines that you're not
Yes.
happy with.
Oh, so
Okay.
sorry. I didn't hear.
That's okay. That's okay.
anything.
Don't worry. Don't worry. And you see that
And
maximum will be above 1000 Kelvin, which is
yeah.
practical for like solid iron rather than exotic materials. Okay. Let's. What else you want to show?
And this magnetization.
Really good. So until this 1200, it's very magnetic, right? And then it becomes so it's phase transition from ferromagnetic to paramagnetic due to the heat. So and the states are quite.
Yeah. And finally this.
This
So
is
this
energy.
is this also the
Energy.
magnetization?
No, it is energy. Sorry for
Yeah, okay.
I didn't label. It's energy as function of temperature.
Oh yeah. So I have to discuss this too in the
Yeah.
discussion part of the report. Okay.
Yeah. So please copy paste images. Do screenshot of the images and place them into like Word or PowerPoint, so that they stay with you. They stay with you even after you finish using Matlab.
Okay.
Okay. Any questions?
No, I just wanted to know what I should write for the discussion part specifically.
Just describe how these figures were obtained and what you see, how you interpret them.
Yeah. Okay. Thank you.
And there I will set up. You can stop sharing if there are no questions.
Okay. Wait.
Chamala, is it okay if you stop sharing?
Yeah. I'm just yeah.
Okay.
Wait. Stop share. Stop share.
So here is the calendar. The written reports will be due in class on May 5th, and maybe I will use yes, I will use the lecture time on Monday, May 3rd to give. We have class, right? It is not May 30th is a class. So I will give instructions what to put in the report. So assuming that by this time all your data will be collected and you have some maybe ambiguity of what to write there, I'll provide some suggestions. Okay, so Sohi, would you like to share?
Yes. Is it okay that if I share it, you're
Yes,
gonna be okay. Can you see my pictures? And
yes, yes.
okay, this is online, so it's a little bit different from the program. So I need to do DOS when the spin interaction is negative. So I made j equal negative 0.0001. And I think figure 5 is DOS, which is I need to present, and I got picture like this.
Okay, very good. So please, do you know how to extract these figures into PowerPoint or into Microsoft Word?
Yep, I know. I did last time.
Yeah, please do. Please do.
Okay.
Any questions?
No. Then if okay, maybe I will watch your recording again, and if I have a question, can I send you an email?
Please, please, and send emails that we finish class in a few minutes. It doesn't mean that.
Yeah, I know. Yep. So that's why
around.
I wanna do that later.
Okay, and then you can stop sharing.
Okay.
Payment, would you like to share a screen?
I would like to, Professor, but I'm using other PC for using Matlab, so I'm trying to join using other accounts. So I think you need to let me in. I need your approval. Am I right?
Okay. No, there is only one payment. Let me follow what Crystal taught me. Advanced sharing options. Who can share? All participants. Yep. I think you should be able to share.
Yep.
So it's not about sharing. I'm trying to join the Zoom using other accounts.
Yeah.
Oh, it will be too long. I need to log in and insert you into the send invitation. Right now it will be too long because we need to finish pretty soon. There is a meeting that I cannot skip. It's like duties. So as I remember, Eamon, Xinyang, and Tyler are doing scan of magnetic field. So it is modification of the code. So if you have some questions or your results do not work as needed, it is normal because we didn't discuss in detail. So today the day was devoted to Sahih, Crystal, and John. Next Wednesday, I will focus primarily on the projects for Xinjiang, Cayman, and Taiwan. Okay. So let me quickly check. Tyler, would you like to share a screen?
Yeah. Let me share my screen.
So, do you have any figures?
Yeah, I do.
Okay, show another one.
Oops.
Okay, yep. So there will be more figures generated with adjustment of the code for scanning magnetic field instead of temperature. But just in case, if something happens as a backup, try to save a couple of these figures into PowerPoint or Microsoft so that you have some reference point. Do you know how to do it?
Yeah.
Okay. Do you have any emergent questions?
No, I'll email them to you.
Okay. Okay. Then I suggest we finish now. I would like to stay with you longer. I like you and I like this activity, but I'm already late for what I'm doing. So meeting is done. Everyone welcome is disconnect. Send any questions by email and see you on Monday.
Thank you.
Or send me a request for like one-to-one Zoom if needed.
Thank you.
Thank you. I'm going to end the meeting right now.
Okay, thank you.